car traveling at 30 meters per second uses an instrument, which is not shown, to measure the x component of velocity u relative to the car in a vertical profile immediately behind the car. So that's referring to this velocity profile that's shown here. So the car is traveling in that direction, so the wind would be approaching the car at a uniform 30 meters per second, and behind the car they traverse along this vertical line, measure a high velocity up here, and then a lower velocity as it goes down to the ground. The resulting data are shown by the velocity profile below. The profile can be approximated by this equation. So notice this gives the u component of velocity, which is the x component of velocity, as a function of y. And y is the distance from the ground. So 0 at the ground, y increasing upwards. This gives an equation for this line, essentially. So when y is equal to 0, this evaluates to 0. And when y is equal to h, this evaluates to u infinity. So any higher than this point, and we just have that uniform free stream velocity of u infinity. Calculate the aerodynamic drag force on the car, assuming this velocity profile persists across the width of the car, 3 meters, and the velocity is unaffected elsewhere. So that's talking about in and out of the page, so in the z direction. The width of this velocity profile is 3 meters, and beyond that we just have the uniform free stream. Assume the air density is 1.2 kilograms per meter cubed. So most of the given information is just given in this diagram, but we will add to this the u infinity is 30 meters per second, and we have the equation for this line right here. So that's pretty much all the given info. So what we've been asked to find here is the aerodynamic drag on the car. So we want to find the drag force on the car. So because we've been asked to find a force, we know that we're going to have to look at the linear momentum equation. Need an assumptions list, which we'll fill out as we go along. And down here we can begin our analysis. Now let's go back to the diagram and just have a discussion about what our coordinate system and control volume is going to look like. So first of all, this problem, there's actually a coordinate system already given in the problem. And the coordinate system needed to be given because this equation is written with respect to that coordinate system. So y appears in the equation, that's the distance above the ground, and it refers to the u component of velocity, which is the component of velocity in the x direction. So the coordinate system is given for us. Now we want to think a little bit about frame of reference here. The car is traveling at a uniform 30 meters per second that way, so we need to decide whether this coordinate system is going to be traveling with the car or attached to the ground. Now remember, it's okay to have the coordinate system traveling at a uniform speed because that's still an inertial frame of reference. So we can do either one of those. Now remember that this u component of velocity was measured by an instrument on the car. So these velocities are all measured relative to the car. And that makes sense because right immediately behind the car there'll be a sort of a stagnant zone here, and that air will essentially be traveling with the car. So relative to the car, it's not moving. So what we're seeing here is velocities measured relative to the car. So we're going to have this coordinate system moving with the car. So the control volume, which we'll draw in a moment, is moving with the car. The coordinate system is moving with the car. Everything is attached to the car. So now let's look at what our control volume is going to look like. We need to make use of this information that's been given to us. They've told us how the speed varies along this line. So I certainly want to make that part of my control volume. So I'm going to start with that boundary. So that's part of the control volume. Also, we were told that upstream we have a uniform velocity. So if I go far enough upstream here, I know I have a uniform velocity approaching this thing. And that's 30 meters per second, or that was called u infinity. So I want the inlet of my control volume to be where the velocity is uniform, like that. Now, realize the key to these problems is to choose a top boundary for this control volume that doesn't have any flow across it, and I'll talk about why when we get there. But notice that the velocity is lower back here, So the inlet to the control volume needs to be smaller than the exit because the speed of the air coming in is higher. So if we want the same mass flow rate coming in the front of this control volume as is going out the back, we need the inlet to be smaller. So the top of this control volume is going to be joined by a line that looks like this. And that's going to be a streamline in the flow. So there's no flow across that line. As the flow hits the car, the air slows down because of the drag force on the car, and therefore the cross-sectional area has to increase. So that's an approximation of a streamline in the flow. Now the bottom boundary of this control volume, we just want to go right between the wheels and the ground. And we'll see why when we get to a discussion of our linear momentum equation. So that's what the control volume is going to look like. So very important to realize this is a streamline, and so there's no flow across it. Therefore, we have a control volume with one inlet here, which happens to be uniform, and a discharge or an exit here, which is not uniform. So I'm going to label this inlet as 1 and this discharge as 2, and we'll be referring to those numbers later on as we go forward. Now, we've been given this distance here, h, as 4 meters. But the thing we need to figure out before we can really do our linear momentum balance is we need to figure out what this distance is, because we're going to need that when we do the momentum balance. So that distance I'm going to call L. So this distance I'm going to label as L. And the first thing we need to do is figure out what L is, because we're going to certainly need that for our conservation of linear momentum equation. So the way we figure out L is with conservation of mass. Because that's a streamline, and this is the road or the ground, we know there's no flow across either of those, so the flow in here has to equal the flow in there. So we're going to start off with conservation of mass in our analysis. So conservation of mass, the full equation, looks like this. So this is the rate at which mass is accumulating in the control volume, and that's the net rate at which it's flowing across the boundary. Since it's a steady problem, we can cross that off, and in our assumption list we put steady state. Next thing we can say is we have only one inlet and one exit, and the inlet can be considered uniform. So I'll put here uniform inlet. And so when I rewrite this, still have 0 on the left-hand side. The inlet is uniform, so that's just the mass flow rate. So I'll write that, and it's an inlet, so it's negative. So I'll write that as the density times the speed times the area, and the area will just be LW. So L is that height that I just drew on the diagram, and W is going to be the distance in and out of the screen. So that's the 3-meter width of the car. So what that W is. So that's the inlet portion of this. Then the exit portion we have to integrate because it's non-uniform. So we have the density. Notice that this VR dot n, what VR dot n is the component of the velocity perpendicular to our control surface. Well, that's exactly what this is. So for the VR dot n, I can just put in this u. So that is just u, and then dA is going to be dy dz. So dy in this direction and dz in and out of the screen to cover that exit area. And the limits of integration on y is going to be from 0 to h, and on z will be from 0 to w, and that's the same w as this. So this stuff can come over to the other side. And now I can bring whatever's constant out of this, rho. Notice that there's nothing in this equation that depends on z, so I can do the z integral right away, and that will just give me w. And then the integral from 0 to h, so this is my integral with respect to z. I can put in the expression that tells me how u varies with z. So that's u infinity over 2 times the sine of 2y minus h divided by 2h, and that's all multiplied by pi, plus u infinity over 2. So that's all integrated with respect to y. So this is just the equation that was given in the problem, because it tells me how u varies with y. Now notice we've got a density and a w on both sides of this equation. So the density and the w can cancel. Also, we have a u infinity in every term in this equation. So there's u infinity there, and we can also factor constant u infinity out of both these terms. So this u infinity can actually cancel as well. So that gives us our expression for L right away. So we'll just clean this up. We can factor out a 1/2 out of the integral as well. There's a half there and a 1/2 there. So we have 1/2 our integral from 0 to h sine 2y minus h over 2h times pi plus 1 dy. Now we have to integrate this. Now I think what makes this a little bit clearer, this integration, if we do a substitution. So I'm going to let eta, which is just a temporary variable that I'm going to use here, I'm going to let eta be the argument of this sine function. So 2y minus h over 2h all multiplied by pi. That's the substitution that I'm going to use. If I differentiate this, I can see that d eta is equal to pi over h dy. So now I can rewrite with this substitution. So L equals 1/2. We'll talk about the limits of integration in a minute. This is just now sine eta plus 1. And then in place of dy, I put d eta times h over pi. So h divided by pi d eta. So now I'm integrating with respect to eta instead of y because I've done the substitution. So I need to change my limits of integration. If we put y equals 0 here, we get negative h over 2h. So that's negative 1/2 multiplied by pi. So that's minus pi by 2. And if we take h and put it in there, we get h over 2h times pi. So that's just pi by 2. So the limits of integration are converted using this equation here. So now we can integrate this fairly easily. So this is L is equal to h over 2 pi. Just bringing this constant out in front with the half. And then the integral is minus cosine of eta plus eta, evaluated from minus pi by 2 to pi by 2. So that's equal to h over 2 pi, 0 plus pi by 2, minus 0 minus pi by 2. So that whole thing is just equal to h over 2. So that's interesting. Go back to our diagram. What that tells us is that this L is half as big as this h in order to have the same flow rate through. So we've now got the inlet area defined. We can now go to our linear momentum equation to calculate the drag force. So let's consider the linear momentum equation next. So that's the full linear momentum equation. Now we want to think about each term in this equation. The first term is the body force term. So let's go back to our diagram and just see how that comes into play. So that's the weight of the car and even all the air inside the control volume. Remember, it's the weight of everything in the control volume. Well, this direction is g in the negative y direction. Notice we're after a drag force. Drag force is in the x direction. So even if we knew the weight of the car, it's not going to affect the answer. Okay? So I'm going to neglect body force, and I can do that because of the direction. So we'll go down here and cross off the body force. The next thing is the pressure force. So this is the contribution of pressure everywhere on our control surface. So notice everywhere on this control surface is essentially atmospheric pressure. Now there will be some slight changes in pressure back here, but for this analysis we're going to ignore those. So we're going to assume uniform pressure on the control surface. And that allows us to get rid of that term. Next are viscous forces. So again, we go to the surface of our control volume. And notice here we just have air coming straight in, there, straight out. No viscous forces on the bottom here. And this is just a streamline in the flow. So there's going to be very, very small viscous forces there. So I'm going to neglect viscous forces. So I cross that off. Next thing is the reaction force. And again, reaction force is the force by any solid member cut by our control surface. So notice the only thing where that's happening is where the wheels touch the ground. So the reaction force is going to be the force that the ground exerts on the car, because the car is in the control volume. The reaction force is always forces exerted on the control volume. So the force that the ground exerts on the control volume through the wheels is that reaction force. So notice that's what we're trying to find here. If we were to think about a free body diagram of the car, just draw a temporary one over here, there's essentially two main forces acting on it. There's the aerodynamic drag force, which is what we're trying to find, and there's a force in that direction due to this reaction force, due to the force that the ground is exerting on the car through the tires. So this is what we've been asked to find. Our linear momentum equation is going to give us this. Be exactly the same, just in the opposite direction. So we need to certainly retain that in our equation. So going back to our linear momentum equation, we're going to keep that. That's what we're trying to find. When we did the conservation of mass analysis, we already assumed it's a steady problem, so that can be crossed off. And we already talked about the fact that we have a uniform inlet and a non-uniform exit. So that'll have to be taken into account when we write this term out. So just cleaning this up, we have our reaction force alone on the left-hand side. We have our non-uniform exit. So I'm just going to say we're integrating over exit 2, density times velocity times v dot n dA. And then our uniform inlet we can write as minus m dot times v1, the velocity at 1. So we just need to consider the x component. So I can factor density out of this, assuming the density is constant, which we should put to our assumptions list here. Double integral, and we'll come back and put the limits of integration on that in a moment. Now, notice that v dot n we've already talked about. That's just our expression for u. But this now is just the x component of this velocity, because we're just taking the x component of this equation, and that's also u. So that and that are the same thing in this case. So we'll just put our expression for the velocity at the exit, which we've seen before in conservation of mass. It's that, but we need to square it because there's that multiplied by that. And then our dA as before is dy dz, and as before the limits are 0 to h and 0 to w. So that's our exit. Then we have a uniform inlet, so it's negative. The mass flow rate is the density times u infinity times w times L, so that's the mass flow rate, but then we need to multiply by the velocity again to account for this. So notice that here v1 is shown as a vector because we're still considering both components, but the velocity at 1 is only in the x direction, and its magnitude is u infinity. So that's why that shows up there. So we can factor some stuff out of this. We have our density out front already. Notice there's going to be a u infinity squared in every term. So I can factor out the u infinity squared. W I can integrate right away because nothing in there depends on z. There's also going to be a 4 in the denominator of every term, so I can factor that out. And what I have left is my integral with respect to y, so that'll be from 0 to h. So I'll multiply this out because remember this is squared. So I'm going to have a sine squared term, 2y minus h over 2h times pi, plus 2 times a sine term, and then plus 1, because this term I've factored out the u infinity and the 2, and so that's just going to be 1. So that whole thing times dy, and then can't forget our inlet term here, minus rho w u infinity squared, and then the L I'm going to substitute in h over 2. So we use exactly the same substitution as we did when we did conservation of mass. So we're going to let a temporary variable here, eta, be equal over 2h times pi, and then d8, and then d eta will be pi over h times dy. So now I can substitute these into here and carry out the integration and substitute in the limits. So we'll do that next. So now we're ready to substitute numbers into that. So that's our density. W is 3 meters. U infinity is 30 meters per second. Got to remember to square that. And then the h is 4 meters. So that works out to negative 1.62 kilonewtons. So the drag force, remember, is in the opposite direction. Certainly makes sense that it's in the positive x direction. That's to the right. So